Okay, in the last video clip, we mentioned that we wanted to actually go back and do a quantitative calculation for the lag time of a set of moving clocks. In other words, when an observer like Alice is looking at a set of Bob's clocks that are moving past her, or the other way around, if Bob is observing Alice's clocks, then the front clock lags in a sequence of clocks as it's moving past. And so we did the qualitative argument earlier in the course just to get the idea and the principle to remember that the front clock always lags. And now we want to find out exactly how much it lags by. And so let's set up the situation here. We've got Bob's ship is what we're going to be focusing on. And he has two clocks, one at the front and one at the rear of the ship, and a special apparatus that can shoot light beams out in both directions. And the length of the ship, as far as Bob is concerned, is L sub b. And again, also as far as Bob is concerned, he's at rest. He's not going anyplace because he's in his frame of reference. He doesn't see anything moving around him. He sees the ship just there. He can't tell whether he's moving or not. He assumes he is at rest. So length of the ship is L sub b. His front and rear clocks are synchronized. He's done that in advance according to him. And this little device that shoots out light beams will shoot them out simultaneously, one going toward the front, one going toward the back. Since, as far as Bob is concerned, nothing is going on. He's not moving or anything. He sees the frontward going light beam traveling at c. It hits the front clock, and maybe, again, flash photograph goes on, takes a picture of that clock. At the same time, the rearward going light beam is traveling back and hits the rear clock. This is exactly positioned in the middle of his ship, and so clearly to Bob, the two light beams are going to trigger the flash photographs at the back and front of his ship at the same time. Everything is synchronized, so there really is nothing too interesting going on as far as he is concerned. Now, though, let's look at Alice's perspective, observing Bob's ship, and we will assume that Bob is moving left to right past Alice, as we've done before. So she is seeing his ship moving with velocity v in the positive x direction. She sees his rear clock and front clock. As before, she sees the light beams get shot out, and we'll get back to those in a minute. Note that the length of the ship to her is L sub a, which is not necessarily going to be the length of the ship to him, because remember, we have length contraction. So we're going to use length contraction a little bit later on here, but for now we'll just say, Bob measures his ship at L sub b, some value. Alice's perspective could be, although we know it isn't, but her length for the ship is L sub a. It could be the same as L sub b, but as we know from previously, this thing called length contraction occurs, and so we'll take that into account, but we'll do that later. For now, we'll just say L sub a is the length she sees for the ship. And the rear clock, front clock, velocity v. Also, we have to remember that Alice is doing all her measurements on her clocks. She has her own measuring stick with all the clocks. There's Alice's. Alice is sitting in her ship. Perhaps as far as she's concerned, she's the one who's at rest. It's Bob who's moving past her. And so she has all her lattice of clocks there, and they're all synchronized in her frame of reference. So that's what she's going to do the measurements on. She's going to take flash photographs when the two light beams hit Bob's front and back clocks, and then she can do the calculations in her clocks and see what she would see on Bob's clocks at that point. Again, as far as Bob is concerned, there's nothing really too interesting. As far as he's concerned, clearly the light beams hit the clocks simultaneously. The clocks are synchronized, therefore they'll stop at exactly the same time, or the flash photograph will occur at exactly the same time on each of them. But let's see what Alice's perspective is. And really the key part here, as we did qualitative the first time, is that the speed of light is constant to all observers. Okay? And if it wasn't that way, then as the velocity was going that way, the light beam here would take account of that velocity and so it'd slow it down and speed it up for the other one. But in actual fact, Alice sees the speed of light, SC. It does not change. You don't add the velocity v or subtract the velocity v from these light beams. They're just still c. And so what happens here, as the front of the ship moves off in that direction by velocity v, it takes this light beam longer to get to the front clock than the backward going light beam to get to the rear clock, because the rear clock is getting closer to that light beam as it's traveling toward it, and the front clock is traveling away from the frontward going light beam. So qualitatively, we can see there is a difference there. What we'd like to do is figure out quantitatively what that might be. So we're going to erase Bob's picture here, because again, that's fairly standard, and we still have Alice's version over here. And do a little calculation here to see if we can figure out what's the actual difference that Alice sees in terms of this lag time. We know the lag time occurs. Now we want from previous arguments we made, previous examples. So now let's see if we can actually calculate it. So from Alice's perspective, let's look at the rearward going light beam first. Okay? And let's imagine that the ship is traveling along here a little bit, and she sees then a little bit later in time the leftward going, the rearward going light beam hit the clock. And let's say it just occurs, this has moved on a little bit here. Let's say it occurs, let's do it on this one right here. Okay? So she sees at that point in time, she'll see a value on her clock, T sub A, and we'll do rear there. We'll rewrite this in a second here. But the idea is, at this instant in time, she sees the light beams go off, ship is traveling this way, and then say, oh, okay, this light beam triggered the flash photograph at this point, and on her clock, her set of synchronized clocks, they all read the same thing at this instant in time. For her, T sub A rear is the value that she sees on her clock there. Okay? Well, can we do a little calculation of that? Just distance over time type of calculation? The answer is yes. We know, for example, that the distance, so let's look at the rear, we'll call it the rearward light beam. The light beam heading toward the back. Distance covered is going to equal what? Well, we know that the length of the ship is LA to Alice, so it's going to cover half the distance here minus the distance the ship itself has traveled. So it's going to be LA over 2, the length divided by 2, but the back of the ship has been moving forward here by a value v times whatever time it took to get there. So we get something like this. The distance covered is going to be half the length of the ship minus the velocity times T sub A rear. Okay? That's a little unfamiliar to you. Just sort of ponder that a little bit. It's clearly half the distance of the ship, but then half the length of the ship, but the rear part is moving forward. Well, how far does it move forward in the given time until this is triggered and it hits the clock there? Well, it's simply the velocity of the ship times that amount of time until it hits the backward or the rear clock there. Okay, so that's the distance covered. And the next question is, how much time does it take to cover that distance? Well, it's a light beam. It's going at speed c. So the elapsed time for the rearward light beam is simply the distance covered, the distance it has to travel. Maybe distance traveled would be a little more precise here, but distance covered divided by the speed of light. Okay? But what is the elapsed time? The elapsed time is TA rear. So here's what we've got. We've got TA. Again, this is all from Alice's perspective. She sees the light, the rearward going light beam go off. She sees them both go off simultaneously. Sees this one go this way. The ship is moving that way a little bit. It hits the rear clock at this point on her clocks, t sub a rear, whatever that happens to be. So that time is the distance covered from here to wherever it ends up, divided by c, the speed of light. Well, what's the distance covered? Distance covered is simply this. So here's what we get an equation that says this. We say TA, the value on Alice's clock, is this distance covered here. So it's L sub A. I'll write this a little bit bigger here. LA over 2 minus V times T sub A rear all over C. Now let's look at what we have. We have LA. Alice can get that value by measuring Bob's ship. From her perspective, velocity we know. We've got speed of light. TA rear appears here, it appears here. That's really what we're after. I want to find what is the elapsed time on Alice's clock here. And if actually it's fairly simple algebra, we won't do it out here. We'll leave that as a little exercise, practice exercise for you to do. If you do that, here's what you find. You find, so you can check your answer here. We can find Alice's clock when, so this clock here, when the rearward going photon hits the rear clock on Bob's ship, is LA over 2, 1 over C plus V. Okay, so we'll go from there to there, a couple lines of algebra. Okay, so we say, great, we've got that part. And then, of course, as we've been arguing qualitatively, she has to wait a little bit longer for the frontward going light beam to hit Bob's front clock. And so maybe that occurs a little bit later on in terms of her lattice of all synchronized clocks here. And so maybe, we'll go out maybe even to our far one here. That occurs at, we'll call that T sub A front. And again, at that instant in time, all of Alice's clocks say TA front. They're all synchronized, so it's 0, 1, 2, 3, boom. Rearward one hits, record that, wait a little bit more here for the front going photon to catch up to the front clock, and boom, at that instant in time, do the flash, it'll read TA front. Where TA front here is going to be a later time than TA rear. Okay, we can see that qualitatively. We want to figure out quantitatively. So let's now do the similar type of thing, but for the frontward going beam. We'll leave this one right here because we'll use it in a minute. That was our first result. Okay, so for the frontward, light beam, it's really the same idea here. The distance covered, distance traveled by it, will be equal to what? Well, it's again, it has to go half the length of the ship, LA over 2, L sub A over 2, plus a little bit more because the front is traveling away from it. And that little bit more is going to be the velocity times however much time it elapses between when the light beam was shot and it actually gets there. So it's going to be LA over 2. That's the half the ship plus the extra part. Last time this was a minus thing because minus sign because the rear was getting closer to the light beam, the rearward going light beam. So it's plus V times Alice's clock reading when it hits the front. So that's the distance covered. The elapsed time, just like before, is going to equal the distance covered divided by the speed of light, because we're talking about a light beam. That's how fast it's going. So it's just basic distance formula here. Distance covered divided by speed gives me my elapsed time. If I have to go 60 miles and I'm going 60 miles an hour, 60 miles divided by 60 miles an hour gives me 1 hour for my elapsed time, and so on and so forth. And the elapsed time, though, is simply TA front. That's the elapsed time between when the light beam is shot out of here and when it actually reaches the clock. And this is all according to Alice's measurements on her clock. So I get just very similar to before, TA front equals the distance covered, which is LA over 2 plus V T sub A front on Alice's clocks, all divided by C. And if you do that, so notice we have TA front on this side, we have TA front on this side, we have V, which is a given value, C, we know LA is a given value, the length, according to Alice of Bob's ship. And again, you manipulate a little bit, doesn't need too much algebra, get the TAs on one side, and you will find out that, we'll write it up here because we'll want to see both of them here in a minute. We find out that TA front equals, very similar to what TA rear is, but not quite the same. It's LA over 2 times 1 over C minus V. So there's a C minus V here instead of a C plus V in the first case. And note also, just to check this, I've got LA over 2 in both cases. 1 over C minus V compared to 1 over C plus V. This is going to be a smaller number than this. Right? I'm taking C and subtracting the some other velocity from it. So this will be a small number. 1 over that will be bigger than if I add the velocity. And that makes sense. If we got something else, the opposite of that, it wouldn't make sense because we know TA front is later in time than TA rear. This is saying that the value of TA front is bigger than the value of TA rear. So that checks at least. Doesn't mean we could have made some other mistake there perhaps, but at least we did that check and it's consistent. So we're almost there. We say, again, we're thinking about Alice here. So what is the time difference that Alice reads on her clocks between when the light beams hit the front, Bob's front and rear clocks? Well, that time difference, which often we use the delta symbol, of course. So delta T for Alice is going to be simply TA front, the time when the front light beam hits, minus the time when the rear light beam hits. And so what is that? Well, we've got our two equations. So we've got LA over 2 times 1 over C minus V. That's from right there. Minus our equation down there, LA over 2, 1 over C plus V. And if you, again, a little algebra required here, it's interesting what happens is, because you sort of look at it and say, well, there's not much difference. Clearly, I've got an LA over 2. We can pull that out in each case. And then we just have the 1 over C minus V minus the 1 over C plus V. It doesn't look like that would be too difficult or give us some interesting results or anything like that. But here's what happens. I'll leave a little exercise for you to take this and get to the next line here we're going to write down. You can check it against the answer here. Here's what you find. You get LA V all over C squared, okay, times 1 over 1 minus V squared over C squared. Okay, so when you actually, it takes about 1 or 2 lines there to get from here to here. And you look at that a little bit and you say, hopefully this term here reminds us of something. In fact, that is simply gamma squared. Because again, well, let's see, where should we write it? We'll write it over here. Should just have this in your brains by now, but we'll write it one more time here. 1 over the square root of 1 minus V squared over C squared. In fact, that's why we put it in this form with the 1 minus V squared over C squared in the denominator there. So that's gamma. Gamma squared then is simply that square root squared, which just gives us 1 minus V squared over C squared in the denominator. So we could write this as LA times V over C squared times gamma squared. Hey, now we sort of gotten someplace. So that's our result for delta t. Let's get rid of this for a minute. Get rid of that one because we have a little bit more to do here. We say, okay, that means that as far as Alice is concerned, she has the length of Bob's ship. Remember, this is not the length of Alice's ship. We're using LA to stand for the length of Bob's ship as Alice observes it moving by. And c squared, of course, v is the velocity difference, or just the velocity of Bob's ship, really the velocity difference between Alice and Bob, and the gamma squared there. Well, remember we said we'd really like to put this in Bob's terms here a little bit because that's often the easiest way to deal with it. We'll be given Bob's information. Bob will say, hey, I've got my clocks here. They're nicely synchronized. I've got the length of my ship. And we want to know, how does Alice perceive that? Well, Alice will perceive that, again, the front clock is going to lag the rear clock because qualitatively, again, we'll get to the answer here in a second. Qualitatively, we know the photon hits the rear clock first, and we see the value on that, and then it hits the front clock a little bit later on. And the actual value with Alice's numbers in here would be LA, and then c squared v and gamma squared are all just the same for either Bob or Alice. But remember we said the length of Bob's ship was LB, L sub b to him. To Alice it's L sub a. Length contraction applies here. As Bob's ship goes by Alice will see the length of Bob's ship to be smaller than Bob measures it to be. And in fact, LA will be, now remember, you have to think about this because it's easy to get it reversed. We say, okay, we know it's length contraction, so Alice is going to see a contracted length for Bob's ship. We know that gamma is a number bigger than 1. Okay? So LA is going to be bigger than LB, right? Alice is going to see it contracted. Actually, here's why you have to be careful. I said it the other way around here. So LA is actually going to be a smaller number than LB. In other words, LB over gamma. This is why it's just useful to think, okay, length contraction. What does that mean? It means Alice sees the length of Bob's ship to be smaller than Bob sees it to be. And we know gamma is always bigger than 1, and therefore LB divided by gamma will give me a smaller number for LA. So we can plug that into our formula here. Remember, this is the time difference that Alice perceives, that Alice observes between the two clocks. So we've got LA, L sub A becomes LB over gamma. So this becomes LB V over gamma C squared times gamma squared. In fact, I'm going to write it up here now. Okay, so we did all the arithmetic here, so we'll keep the basic formula we want. Let's bring it up a little bit so we can see it better. So we have found now that this equals, and now we can cancel one of the gammas. We've got a gamma in the denominator, a gamma up there, so we get LB V over C squared and a gamma involved here. So put the gamma out there. Okay, so now we have it in terms of Bob's length. But this is very important. The next step is that this calculation is on Alice's clocks. Okay, this is what Alice sees on her clocks when those photos get taken. Really what we'd like to know is what are on Bob's clocks. In other words, when Alice takes those photographs right here, boom, and then a little bit later, boom, she looks at her clocks and sees this time difference, either in this form or a previous form or this form. What's the time difference on Bob's clocks? Well, we just use length contraction. Remember, the other thing is time dilation. Moving clocks run slow to an observer who is observing those moving clocks. So from Alice's perspective, She's just found the time difference on her clocks between when the two light beams hit the front and rear clocks. The time difference on Bob's clocks is going to be less, right? Because Bob's clocks are running slower than Alice's clocks as Alice observes them. And that time dilation factor, again, is gamma, and it's going to be 1 over gamma, right? Because, again, one way we can write this is if we have delta t for Alice, a time length for Alice is going to be, in terms of Bob's clocks, or let's write it like this. It's a little easier to say this way because that's how we've been saying it. For Bob's clocks, a time difference is going to be smaller than for Alice's clocks. Alice perceives Bob's clocks, or observes Bob's clocks running more slowly, and so it's going to be delta t for Alice, whatever time difference her is, divided by gamma. And what we have here is a delta t, a time difference, a length of time, elapsed time for Alice. So to get Bob's version on his clocks, we have to take this and divide by gamma. And therefore, so this implies that the delta t on Bob's clocks is going to be this divided by gamma. And note we have a gamma here. When we divide by gamma, we'll lose the gamma. And so we get L, B, V over C squared. And this is actually what we were looking for after all that. Okay? So again, let's review just what we found here. Qualitatively, we made the argument qualitatively here. We did it before as well, that Alice will see Bob's front clock lagging the rear clock. Okay? Even though to Bob's perspective, they're perfectly synchronized. Okay? To Alice's perspective, they're not synchronized. The hits of the two photons or light beams occur at different times on her clocks. And she sees Bob's clocks as not synchronized. And the front clock lags the rear clock by how much? By this much. If I know what the length of Bob's ship is to Bob, and I know what V is, then the lag on, or the difference that Alice sees on Bob's clocks is the length, according to Bob, times V divided by C squared. So, and this was true then, here we're just using the length of Bob's ship. This is true for any distance where we have something in Bob's frame of reference and converting it into Alice's perspective here. So that if Bob has his whole line of synchronized clocks, his whole lattice of synchronized clocks moving along here, any two clocks on that huge measuring stick of synchronized clocks, when Alice is looking at those clocks as they go by at speed v, she will say, give me any two of those clocks on that line. I'll know the distance between them. So we can actually write this in general as the distance times the velocity over c squared, where d is the distance between the two clocks in Bob's frame of reference. So Bob tells me, hey, the distance is this. I'm traveling at speed v. I will be able, therefore, to figure out how much Bob's clocks are not synchronized from my perspective, the front clock lagging the rear clock by this amount here, this dv over c squared amount. So two things to remember. One is the front clock lags. We knew that before. Now we know exactly how much it lags by. That if Bob tells us the distance between the two clocks in his frame, it's going to be dv over c squared. Now, we went through this really to show that we want the result, of course, but there's nothing too profound here in one sense, but something very profound in another sense. In other words, this all comes from the fact, really three key facts we use. One is we use the fact that c is the same to everybody, that a light beam will always have the speed c. Relative velocities will not affect the speed of light. And therefore, we get the lag time effect. And then to get the actual quantitative value, we use time dilation and length contraction to end up with this. In the next video clip, we'll do a shorter version of this and see how we can get it using the Lorentz transformation, just to verify we can also get it from that as well.